that's what we have learned. Various rules. It's all about rules. A junction rule, a manifestation of a law of conservation of charge when current travels, and splits. Of course, the total number of charge doesn't change, and rules for resistors connected in parallel or in series, and the Ohm's law, which describes how electric current through a resistor is related to the resistance and potential difference. And the question is related to a circuit. The schematic is here, and this symbol represents the battery, this symbol represents a capacitor, this symbol represents a bulb, this symbol represents a switch. Right now, the switch is open. An open switch has infinite resistance. Electrons cannot jump across. So right now, there is nothing happening in it. But if I close the switch, something should start happening. The question is what? So these are answers. Maybe zoom out a little. Yeah. So you should read before I block it. Because right now I'm blocking it and you can't read it. So I'm going to be moved left, right. So, and to create a circuit, we have to use wires. And usually we start from a battery. That's a plus. Now I need to connect it to a switch. People used to call this thing a switch, but technically that's a key, Morse key. You don't know what that means? SOS, which is a song. You know which group? ABBA. 30 years ago. You don't know that. So just connecting everything with wires, and this is a capacitor. I'll tell you what this device is. It just shows that right now nothing is happening. When electric current starts traveling, we can see these red dots moving. That's it. It's a good visualization tool. And well, the switch is open, so I can connect. And when I close the switch, we should start observing electric current. So I'm going to wait a little bit longer. What should start happening? Well, the best way is to, I'm going to switch back for the moment, is to just draw a closed switch. And what should start happening? Well, this is a positive end electrode of a battery. This is a negative. And as we know very well, a fictional positive charges would start traveling away from a positive electrode. And what would be happening on another side? Well, battery is acting like a pump, so it starts moving electrons. So electric current would be like this. If there is electric current, the bulb should lighten up. The question is, for how long? And let's see. This is a very rare occasion in physics where we actually need to think a little bit, because it's not related to just repeating something we've done in the past. It's related to like connecting the dots between different pieces of information we've learned. So that requires some thinking, and thinking is a good thing because it's like an exercise for a brain, right? Like so this whole course is like fitness for your brain. Mine too. And some people like fitness, some hate. So, number three. And let's just see. Now, if you really put some effort into thinking, it doesn't matter if your answer is right or wrong, because you're excited your brain cells, and that action on its own helps to intensify learning process. If you just randomly picked a number, that means you didn't help yourself. And if you don't help yourself, that means you don't like yourself and you're punishing yourself for something, I don't know what, that's outside of this course. So let's see what's going to happen. Where is the bulb? That's the bulb, it is on. So what's happening? Electrons running. How should electron run? Actual physical electrons should run away from a negative electrode, so they should travel this way, then this way, travel this way, run, travel this way, this way. When we close the switch now is like a wire, has no resistance, so, and the electrons keep travel this way. So what do we see here is not a direction of electrons. What we see here is the direction of those fictional positive charges. They would have been traveling in that direction. That is actually a direction of electric current. What happened to the bulb? What happened to the bulb? So if you said it will remain on forever until we open the switch, your answer was what? Wrong. What you didn't take into account? That capacitor has a fixed maximum value it can of a charge it can store, as long as the charge, see, it's getting slower and slower and slower and slower, because the more electrons it has, the harder new electrons to get in. That's it. Eventually it will stop. We still observe some electric current, but that electric current is not enough already to make this bulb bright. It is too low, and eventually it will become zero. So the right answer is 4. But if instead of a capacitor, we would use just a wire or just a regular resistor with the same bulb, and we close the switch, in that case, electric current would travel, well, technically forever, or until the battery would die. Nothing is eternal in this world. Eventually everything dies, as we know. And This is an example when we used information from different parts of physics, something about capacitors, something about the new topic, electric current. And now we can go back for the moment and talk about why capacitors connected in series should have the same charge. See, it doesn't move anymore. Yes?
Is it possible for
Thank you for asking. Bless you. So what do we need to do to answer that question? We have to open the switch, take the battery out of the circuit, close the circuit again, and now close the switch. What is happening? Exactly what you said. The capacitor has stored the energy, but now it's releasing energy back. We don't really need the battery, but what is the difference between the capacitor and the battery? The capacitor, well, see, it's dimmer and dimmer. Eventually it will become dark again. So the capacitor has a fixed amount of energy. When it's gone, it's gone. We have to charge it again. The battery, on the other hand, can provide fixed value of voltage for a very long time. That's it. It has, well, something inside which makes voltage across these two electrodes fixed, no matter what's happening outside. Again, we can see that electric current now, first of all, travels in opposite direction, plus slows down, and eventually electric current dies again. But we can connect the battery again, recharge it, and we could do it again and again if we wanted to. Where does energy come from? From the battery. The battery does work on charges. Those charges get stored in the capacitor. Capacitor has energy. If we remove the battery, the capacitor loses that energy. And the electric current does work. We'll talk about it soon. And that work, well, was even visible for a while. The electric current was strong enough, high enough to lighten up the filament. What did it mean? It meant that the energy stored in the capacitor eventually was transferred into the optical energy, into light, into the photons. And those photons traveling away hit an eye, excite the retina, the neural pulse goes to some places, and that's what we call vision. Well, there's another type of vision when people can predict future. That's outside of this course. So, and now, well, actually, probably we don't need it anymore. Yep, don't move anymore. No electric current. Now, this is what we've talked about before. We know that if we have a conductor can only have the same potential on the surface and inside. There is no electric field inside. Electric field on the surface is perpendicular to it. We know that if we have a large plate with a charge on it, it generates a uniform electric field. So, and now we can use this for a simple model. The general explanation requires some calculus, but a simple model helps to understand what is it about. It's about a single word, equilibrium. in equilibrium, charges, electrons, should move anymore. They might wiggle a little bit due to temperature, but in general, they shouldn't move anymore. Why does it happen? Well, first of all, because of the resistance. Every conductor has a resistance because it has atoms. Without resistance, those electrons couldn't ever stop. We didn't mention anything about the resistance before, we meant it. But now we know when electrons travel through a conductor, they collide with atoms, and eventually they have to give away all the energy. That's the only way the equilibrium can be reached, due to resistance. Without resistance, they would be moving back and forth infinitely long, like a superconductor does, actually. But now, let's say you have two capacitors. Let's make them different. And you attach a battery, let's say like this. What's going to happen? Well, first, this will become positively charged, because what? Because electrons like make them blue, will be collected here. But the law of conservation of charge tells us that the amount of electrons left the positive plate should be equal to the amount of the electrons brought to the negative plate. That's normal. Conservation of charge. What's happening here? This is a conductor, conductive plate, conductive wire, conductive plate. So these positive charges will attract electrons, those will repel electrons, and of course they will move. So we should have electrons here, deficiency of electrons here. So that should be some kind of positive charge, Q plus star. That should be some negative charge, Q. The question is, why should they be equal to each other? Why? This is equal to this. That's what the real question about. And well, you see, we have solved the problem about electric field generated by a single plate. Let's say these two charges are different. In that case, we should have electric, let's make it red, electric field like this. But we also should have electric field like this, two plates, exactly like we did before. And if charges not equal to each other, net electric field outside would not be equal to zero. If net electric field is not zero, it acts on electrons moving, not equilibrium. That's it. Eventually they should lose all the energy, eventually they should stop moving, and that means electric field outside should be equal to zero. That means those two charges must be equal to zero. The key word is equilibrium. That's how I spell it. And again, this is a situation very common in physics. At first we talked about it. I remember what I told you. I told you when electron moved over there, it pushes one electron away. Then second electron moves, it pushes second electron away. It's not a proof, of course. It's a mental trick to help us to remember that charge should be the same. This is more like a proof. It's a simple model, but it tells us the general idea. Why the charges should be the same. Any questions? So we had to go back to use the new material to better understand the previous material. This back and forth in physics happens all the time. All the time. So every time when we talk about something, it's never the full truth. There's something more about that. It's like in politics. But politicians lie on purpose. Physicists never lie about physics. Well, now we're going to talk about batteries one last time. We know what it does. The mission of the battery, well, we know the mission of human beings is to bring order, fight entropy. The mission of battery is bring fixed amount of potential difference. That's it. How does it do it? Well, every battery has inside many, many tiny demons. We call them chemicals. And that's it. There's some special type of chemical reactions which separate the charge. And we always have some extra electrons close to the negative terminal. And of course, deficiency of electrons close to the positive. If we connect some wires, conductive wires to the battery, those electrons will be able to escape. They start moving. But those demons, chemical reactions, will bring more. That's it. Until they die, because as we know, everything dies. And the simplest circuit should have at least one battery and at least one resistor. And again, whether we like it or not, we have to know the slang. The battery has a name, the active element of a circuit. Any device, bulb, projector, motor, any device which uses that electric current to do something has a name, a passive element. And outside of the battery, electric current through the passive element always travels through high potential to low potential. But now, when the circuit is complete inside the battery, this rule actually doesn't work anymore. Inside the battery, electric current travels from low potential to high potential. Why? Well, demons. Maybe angels, I don't know. Chemical reactions. What? Anyway, of course, you can find a lot of helpful analogies online. This is one of those analogies which I personally also like. The battery is like a ski lift, you know. And that fictional positive charge is like a skier. To get up the hill, it has to be some kind of a special work done on it. And then from the hill down the ground, it just slides on its own. And then again, up, some work has to be done on it, and then on its own. And that amount of work which a battery does per coulomb has a name, EMF. Well, people used to call it electromotive force because they thought it was some kind of a mechanical force which leads to electricity. Now we know it's not that what's happening, so the name is outdated. People just use letters EMF or a Greek letter, epsilon. And we know that's supposed to be equal to that fixed voltage provided by the battery. An actual battery, of course, has internal resistance. We neglect that fact. Like actual wire also should have some resistance. We have measured, but it's so tiny, we neglect that. So for us, the battery doesn't have any resistance. Wires don't have any resistance. If we have any resistance, it's here in device, in the passive element. And see what the difference between the passive element and the active element. The active element, the battery, produces fixed amount of voltage. Now we call it EMF. The passive element doesn't produce anything. If you want to produce something, you should be active. That's the rule. Now, if we apply the Ohm's law cannot be applied to the battery. The Ohm's law only can be applied to any passive element, which means to a resistor, to a bulb, but also to a wire. A wire is not a battery. So we can apply Ohm's law to anything which is not a battery. But if wire doesn't have a resistance, R equals 0, there is no resistance, which means there is no potential difference. So an ideal wire doesn't change electric potential. That's it. Where electric potential changes here from high to low. We say potential drops. Sometimes, so potential drop, potential rise, these are just, again, different names for voltage. That's it. So please, tell me what you think. So we have a simplest circuit with one active element, battery, one passive element, some kind of a resistor. The battery has EMF, fixed voltage, 6 volts. Now, we always assume that there is one, in any circuit, there's one point which is grounded. And grounded doesn't go anywhere. Grounded means connected to the earth, which means electric potential of that point is 0. We ground, yeah. So we choose where it's 0. And of course, normally, the easiest choice at the negative electrode of the battery. So this potential is 0, and the battery makes potential here 6 volts higher. And if we want to use the Ohm's law, it has to be applied to the passive element, to the resistor. And to apply that law, we need to know the voltage across the resistor. We need to know this voltage. So we need to be able to make a transition from this to that. Survey says. So you see, your brain is a powerful pattern recognition device. So if you think the answer is 1, you choose 1. The answer is 2 volts, you choose 2. The answer is 3 volts, you choose 3, right? Etc., etc. And what did you say? That should be question 3, so I have to move one question down. One question down, which is 6. I don't think I'm going to say anything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 27 ends here, so these people didn't say anything yet. See, I see 27 answers. I definitely see more people. So just choose any number. Question 3. Enter it, select it. I was always wondering, can I answer the question? That's much better. Still same answer, 6, and of course it is 6. No doubt about that. Well, because wire has no resistance, as we just said, it doesn't change potential. Electric potential along a wire remains constant. So if it is 6 volts here, it should be 6 volts here due to this law. A wire has no resistance, hence a wire doesn't change potential. But how would we measure the potential? Well, let's take a quick look. So we have to measure depending on the situation, we have to measure electric current, electric resistance. Normally, we don't measure electric resistance directly. We usually measure electric current and voltage. We cannot measure just the potential. We can measure only electric potential relative to a specific reference point. So what do we need is a circuit. And wiring circuits is one of human practices which requires some practice. So the easiest circuit, I want to use a bulb. The easiest circuit, simplest one, has 2 elements, one active, one passive. Don't really need the switch, just can connect directly. It's on. And now let's say I want to measure voltage. As we know, there's always the reference point. That's what we call zero potential. And to measure voltage, we need to measure potential difference. And to measure potential difference, we just have to connect the multimeter to 2 different, it's temperature. 2 different points in the circuit. That's why we call it voltage across, kind of. We measure potential difference between these 2 points. Well, if I want to measure, so you see, I don't break the circuit, I just connect the multimeter to 2 different points in the circuit. What do I do if I want to measure electric current? Well, first of all, I need a different device. This one doesn't measure current. How do I know? It says does not measure current. That's why we bought a new one. What is a current? Electric current, what is it? It's a number of charges traveling per second. So if I want to measure electric current, I need to make sure electrons traveling through this device. There is another demon in it, which counts first, second, third, and then multiplied by 1.6 times 10 to the negative 19. That's how electric current is being measured. But in order to do that, we have to make sure electrons travel through. So we have to insert the ammeter into the circuit. In that case, we have to break the circuit first. And then we have to complete it. Now we can read the number, milliamps, and a minus. What does it mean? It means that if I switch these wires, it will be positive. That's what it really means. And when it is positive, it's positive when electric current goes into the red and goes out from black. That's it. That's it. And if you know how to use these devices for a simple circuit, you know everything about these devices. The circuit might be more complicated, and you still will be able to measure voltage, current. If you know voltage and current, you can calculate resistance using Ohm's law. And for more complicated circuits, you can actually prove our relationships for resistors connected in parallel, resistors connected in series. So this is how we measure voltage. Basically, it is measuring a potential relative to zero potential of our choice. This is how we measure electric current. Oh, well, it's coming back. It just takes probably a long time. It has to be this one. Now it takes too long time. That's why I don't like this room. Since the installation, this room was acting funny. I would ask anybody who understands Russian to leave a room for 5 minutes and come back. This is for IT. You see? That's how you scare it. Well, as we know, electric current does work, and we use it every day. For example, we use it right now, air conditioning, projector, computer. And to calculate the amount of work, we just have to apply the same equation we've used before. Electric charge travels through a certain amount of potential difference through certain voltage, charge times voltage, work done by electric field. The energy comes from the source. It could have been battery or maybe a power plant somewhere else. That energy is being transferred. Amount of energy, of course, is lost to environment, to heat, but still some amount left sufficient to be used. And the reason for electrons doing work again is just colliding with atoms. When they collide with atoms, atoms start moving a little bit faster, more collision, faster motion, and we know that temperature is just basically kinetic energy, average kinetic energy of moving atoms. So when they move faster and faster and faster, energy goes higher and higher. If it's high enough, we can lighten up a filament in the bulb or do something else. And if we calculate the power is work per second. So this is the standard expression for electric power. But if we use the Ohm's law, again, we can rewrite this expression using the resistance and the current, or resistance and voltage. It depends on convenience, basically. And now we can solve this problem. How much energy does the filament dissipate in 10 seconds? Well, electric power. So in this problem, we know all variables. We know voltage, we know current, and we know resistance. So it doesn't really matter what equation we want to use. first, second, third, the result will be the same. So the fastest is just electric current is 0.4, and as we know, we have 2 batteries, so that's going to be the power 1.2. A unit of a power is watts, and the amount of energy or work done inside that filament should be equal to power times a time. Power times time, 1.2 times 10 seconds. If we had minutes or hours, we would have to convert it into seconds. So 1.2 times 10, 12 joules. Now again, see what's happening? W. We need to know the difference, right? Here, it's a unit of power, watts. Here, we're calculating work done by electrons on the filament, inside the filament. Any questions? What should happen? So this bulb is on, we've seen it. What should happen to the brightness of this bulb if we remove one battery? What do you think? What do you think?
The power will be half.
And what will happen to the brightness of the bulb? It's going to be dimmer. If we add extra battery, it will be brighter. So if we talk about brightness of the bulbs, and there's some problems like that, it's all about power. More power, brighter bulb. Less power, dimmer bulb. No power at all, it's just dark. And we will have some examples like that. So this is things which kind of handy to remember, put in different memory cells. Yeah. We know everything from this slide, but we should just practice using this knowledge to solve different problems. Battery has no resistance, provides fixed amount of voltage, which is called EMF, which is work done by the battery to move 1 coulomb. And wire has no resistance, so a wire doesn't change potential. And if a resistor has no current, which means it's not connected to anything, if we try to measure potential difference, it should be 0. It doesn't change. Potential only changes when A, electric current is not 0, and B, the resistance is not 0. When charges travel through the passive element, in that case, potential changes. And if we want to calculate power or amount of work, we know what to do. Question? I want to do this. What we have here is a battery, a passive element resistor, a switch. Can I measure voltage or current when the switch is open? What do you think? If the switch is open, can I measure things? No. What do you think? Can I measure if the switch is open? I'm going to risk again. Can I measure voltage? You say no. And why can't I measure voltage when the switch is open? Oh, shoot. Is it forbidden? Is it on? Do I have wires? Do I have hands? So what would stop me from measuring? I just need to complete the circuit. So if I ask again, can I measure voltage when the switch is open? What should be the answer? Yes? It's up to me. I wish I would be paid for that more than I am. Well, the switch is open. If we close the switch, there's a current, it's on, open, nothing. So how should I measure voltage across the switch if I connect these wires like this? Not sure if you see. What does it say? 6 volts. 6 volts. But did I measure voltage across the switch? No. So how should I measure voltage across the switch? I should connect these two leads, wires, probes across the switch. Now, let's see what you said. If you said 0, please raise your hand. Don't be scared. 2. Yeah, why would it be 2? 6. 12. If you didn't say anything, you should say something right now. Well, the answer is work. See? You have to command it. In this rule, that says a wire doesn't change potential. So right here, this, well, we always can set this to 0. It doesn't change a thing. So electric potential here is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Stop here. V equals 0. Well, V1. Electric potential here is 12, because it should be 12 higher than 0. That's what the battery does. This is V minus, V plus should be equal to V minus plus EMF, which is 0 plus 12, 12. Now 12, 12, 12, 12, 12, 12, 12, 12. Up to here it's 12, no doubt. What is happening to the potential inside this resistor? That's the most important question. What do you think? If the question is, what is happening? We only have two answers: nothing or something. That's just pure logic. If you say something, then you only have two options. Potential might increase or decrease. So, please, anyone, tell me what you think. What is happening to the electric potential inside this resistor? What do you think? Yes? So, nothing or something? Nothing. That was another rule. When a resistor has no current, the Ohm's law says this resistor is not 0. R is not 0, but when the switch is open, electric current is 0. So this potential difference should be equal to 0 times R, which is 0. So electric potential does not change, still 12 right here, still 12. And after that, the wire again doesn't change potential, 12, 12, 12, 12. Electric potential here is 12. Potential difference between 0 and 12 is 12. Well, in my experiment, this battery is 6. I should change this slide. I should have changed it many years ago. I don't have battery 12 volt. So, but in my experiment, if I connect, I should read 6. Any questions on that? This method has a name, tracing a potential. We trace a potential. This is the most general method. It can be applied to any situation. If we're familiar, confident with that method, we can solve any problem from now on to ahead. Yes?
So when the resistance is not
There is a simple way to see it. I want to measure voltage across this dim bulb. Oops. Too soon. And what do I see? Nothing. Because there is no electric current, this bulb doesn't, this resistor doesn't change potential. Only with electric current inside, electric potential will change. So we will see difference. What's going to happen if I close the switch? See? It's not zero anymore. Because, well, it's negative. We don't like negatives, we don't like fractions, we don't like square roots, we don't like many, many things. But we always know how to get rid of those. For example, if you see it's negative, just switch, it becomes positive. And now you can see the voltage across this bulb is not zero because this bulb has a resistance and electric current traveling through. And resistance times current is voltage. But what do you think I should see if I measure voltage across the closed switch right now? The switch is closed. The current is traveling through it. What do you expect to see? Zero. Because the switch has no resistance. It becomes a wire. So a current is not zero, but the resistance is zero. Current times zero, zero. Cool. Consider to switching to physics major. You're going to play with this every day. Well, 12, as we know, 0, and question. Anyone want? All right. Question. What do you think about this situation? This is the question number 5. What we have here is a battery and 2 bulbs connected to it, and they have different resistances. This is, let's say, 7 ohms, and this is right now 100 ohms. So what did you say? The gentleman in the 3rd row, 1, 2, 3, 4, 5th chair from right. All right, I'm going to wait until you say something. We're all going to wait. You should pick one. You see, I'm putting the pressure on you. How good are you under pressure? 5. Let's see what everybody says. Most people says, what question is it? So we have a, that can't be right. That can't be right. Okay, A wide distribution is a sign of thinking, and well, how do we call this particular connection? How? Serious. Yesterday we had a rule about connection in series. What did we say yesterday? So why did you say it differently today? Okay, you didn't. Well, so this is not a new question. This is a review. The two elements could have been three or more, connected one after another. That's what we call in series. So they must have the same current. It doesn't depend on the resistance. The question is why. So again, there is a model which helps us to remember this fact. Electric current is not just the number of electrons traveling through. It's a number of electrons traveling per a second. And the number of electrons inside a specific device per meter or per cubic meter, per cubic centimeter might be different. Electrons might be packed up denser or less denser, but also they might move slower and faster. And so if you look at this picture here, we have very dense electrons packed up. You see, spacing is short, but they travel faster. Here we have less dense electrons, but they travel slower. But electric current is the number of electrons traveling per second. So here and there, electric current will be the same, twice of that. So when electrons travel through, they balance density and speed in such a way, so this product, which is current, remains the same. They might slow down, but in that case, we have more electrons per cubic meter. They might travel faster, but in that case, the density is lower. So they balance it up all the time because electrons are very smart. So, and when they travel through all devices connected in series, not number of electrons, but number of electrons per second, which is electric current, remains constant. Now, tracing the potential. From now on, we're just going to solve more and more different problems, answer more and more different questions, nothing really new left to learn. This is an example of a simple circuit. It has one battery and two resistors. Yeah? And the first thing to do is to redraw the circuit. Just draw the circuit, a battery, first resistor, second resistor, I missed it. All right. A battery, the first resistor, the second resistor. All right. Is it a different circuit or the same circuit? The same. It doesn't matter how we draw the wires, because it doesn't matter in the real space how all these elements related to each other. Battery, bulb, okay, we can turn it on. If I move everything like that, it's going to be the same circuit or different? Same. If instead of a short wire, I'm going to use a very, very long wire here. And I'm going to do it like this. Is it a different circuit? The same. So it doesn't matter how it looks like. What matters is how we connect them. And here, what we have is unknown EMF, I suppose. Yeah, we know what we know: electric current. I is equal to 0.1 amp. We know the resistor number 1 has the resistance of 10 ohms, and number 2 has a resistance of 20 ohms. That's what we know. And this picture actually shows a model of what's happening to electric potential. Yeah. So let's say we have that fictional positive charge, not an electron. How do I know? Electrons are blue. So electrons would travel away from a negative terminal, but the battery kind of picks up the positive charge and brings it over here, and then they start traveling away from plus. That's it. Electric current I travels through all elements, and as we just said, it has to be the same inside each element, inside the battery, inside the first resistor, inside the second resistor. What is happening to electric potential? Well, first of all, we can always choose any point we want and ground it. So we make this potential to be equal to 0, which means this potential should be equal to, we call it a plus, should be equal to the negative plus EMF. That's what battery does. It brings the potential higher by its own EMF. So that's 0 plus EMF. EMF still doesn't help, still unknown. Well, but we know what is happening to the potential. We know how to trace it. EMF, 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 EMF. Right here, it's still supposed to be the same unknown EMF. Now, we should ask a question. What should happen to the electric potential inside the resistor? We have only two possible answers. Nothing or something. What do you think? Nothing or something? Something. It drops. This is where we use the Ohm's law. The Ohm's law says if you have electric current traveling through a passive element, the potential difference between the ends of this element should be equal to this product. And electric current always, through the passive element, always travels from a higher potential to a lower potential. So we can call it V right, V not right. In that case, V right should be higher, greater than V not right. So potential drops in the direction of electric current. Electric potential drops. This electric potential right here, electric potential should be equal to what? Well, we can write the law. Ohm's law says potential difference. Well, actually, let's call it, I don't know, middle, because this point is in the middle between two resistors. And you can call it anything you like. Could have been between. So this potential difference should be equal to electric current times the resistance, which actually is a number. Electric current equals 0.1, and the resistance of this resistor is equal to 10, 1 volt. Well, middle. Still doesn't help. So moving on. This potential doesn't change along a wire. Now, so here we still have exactly the same potential. Now, inside this resistor, what happens to the potential? Nothing or something? Something. Exactly. We know electric current is not zero. Resistance is not zero. Electric potential must change. How? Electric potential always drops, decreases in the direction of electric current. To which value? To this value. And this value is 0. So we can apply the Ohm's law for the second resistor. This difference should be equal to electric current times, that's what I have noticed. That's supposed to be a lowercase r. So that's supposed to be 0.1 times 20, 2 volts. Well, now we know this number. And finally, we can use this number where? Back to here. So EMF minus 2 equals 1. EMF equals 2 plus 1, 3 volts. This may be not the most efficient way to solve it. The most efficient way would be actually going in opposite direction. We would calculate this immediately, then that, done. But this is a good illustration of what tracing means. We could have traced it backwards, of course. Doesn't really matter. Any questions? This problem is the root of all problems in the world. That's not a question. Let's just, again, practice. So, one battery. For one battery, we always set negative electrode to 0 potential, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This number tells us that potential should increase by 2 volts. So potential here should be 0 plus 2, which is 2, and 2, 2, 2, 2, 2, 2, 2, 2, 2, still 2. This is the voltage across this resistor, which means this electric potential should be higher by 8. So what it means, 2 plus 8, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. This potential should be higher than 0 by 12. 0 volts, 12 volts, 12, 12, 12, 12, 12. This is a very hard word. 12. So what's supposed to be the voltage across this resistor be equal to? Well, that is literally difference. 12 minus 10, 2. And actually, so high, low electric current. We know a rule. Electric current through a resistor always travels from high to low. So that's supposed to be just some kind of a resistor, a bulb maybe. But in this situation, that's wrong. I'm just going to go to the answer. If we trace potentials in the same way we did, we get 14 and 12. The voltage still 2. However, the direction is wrong now. Electric current still travels, well, It's very important to be able to describe correctly in words what is happening to electric current. The question is where? Electric current through this resistor travels. Electric current through resistor travels. How do we call this direction? Up. Exactly. That's how we should say it. Electric current through this resistor travels how? To the left. Now, electric current through this element travels down. Electric current through the battery travels to the right. And now we say electric current in the circuit is clockwise. And we need to be able to match those individual directions through each individual element and the direction inside the whole circuit, because that's what people say. What is the direction in the circuit? Clockwise. What is the direction of electric current through this element? Down. But it also means, see, this potential is 4, this potential 12. It also means this electric current travels from low to high. That only can happen if this element is not a resistor, not passive, active, which means this is supposed to be a battery. This circuit has 2 batteries. Well, this is a very straightforward example. What do you see here? How do we call this? Series. We said that word, we immediately write the equation R equivalent is equal to R1 plus R2, 6 plus 3, 9 ohms. So the equivalent circuit should have the same battery, but a single resistor with the resistance of 9 ohms. And for this circuit, we know how to calculate electric current. We just have to apply this Ohm's law. Yeah, we know 0, 0, 0, 0, 12, 12, 12, 12. If we have only one passive element, only one active element, the voltage across the passive element always will be equal to the EMF. Electric current always equals this over that. So 12 over 9, 4/3 amps. But now we can go back to the original circuit. We know that the same electric current should travel here. So if I want to calculate the voltage across the first resistor, I can apply the Ohm's law again. It should be equal to current times the resistance of the first resistor, 4/3 times 6, 8. Oops, what happened? I know what is happening. It punishes me. My fours are not perfect. It's Wednesday, it's supposed to be perfect. 8 volts. Now we have a choice. If we want to calculate this voltage, we actually have 2 different ways to do that. First of all, we know that if we have 2 elements in series, this voltage plus this voltage should be 12. So 8 plus something is 12. That something equals 12 minus 8, 4. Or we could have used again the Ohm's law. So delta V2 on one hand, EMF minus delta V1. On another hand, supposed to be equal to same current times R2, 4/3 times 3, 4. Power. All right, we can calculate the power dissipated into the first resistor. We can calculate the power in the second, or total. P1 equals I1 delta V1 4/3 times 8 watts. P2 equals, sorry, and don't, well, okay, that's actually a good thing. I2 delta V2, but current is the same, only voltage is different. How can we calculate total energy? Well, total power, P1 plus P2, of course. However, where does that energy come from? From the battery. So that also should be equal to EMF times current. Again, we have more equations we could use. And this is just 12 times current, 4 divided by 3, which is consistent with this. If we add 4/3 times 8 and 4/3 times 4, it's 4/3 times 12. All right, same situation. The only difference is sometimes we have to solve a problem when instead of a battery we use maybe a power outlet or a generator. So electric current might change in time. We don't care. There is always a value which not average square, doesn't matter. It has a name, root mean square. And again, doesn't matter what it means, it's just RMS. So as long as we know this value for a changing voltage, a changing current, 6 volts, we can apply all equations which we were using for direct current for DC, nothing changes. So here the circuit has a battery, kinda, yeah, in quotes, 6 volts, and 2 resistors, 1, 2, R1, R2, and of course the first intention is to replace these 2 resistors with a single one, R equivalent, and of course we know what to do. We just have to apply a rule for resistors connected in parallel, and that is 1/4 plus 1/8, which is 3/8. What do we do now? Flip it. So R equivalent is 8/3 ohms. 6 volts. So as long as we get the simple circuit, 1 active element, 1 passive element, that's it, we can start applying the Ohm's law immediately, directly, the fastest way to do it. So electric current here, actually, this is my plus, this is my minus. So electric current in this circuit travels counterclockwise. Electric current through my element travels to the right. Electric current through the battery travels to the left. And electric current will be equal to this voltage, which is equal to EMF, which is equal to root mean square, RMS, which is equal to 6 divided by the equivalent resistance. So 6 times 3/8. Uh, 9/4, 2.125. Yeah. But now we can go back to the original circuit. What's happening here? Electric current travels and splits. The junction rule says I1 plus I2 supposed to be equal to I, which is 9/4. However, now we don't have to use it. We could have do it in the first place. What do we know about the voltage across each resistor? Same. So I1 supposed to be equal to delta V1 over R1, but delta V1 is just EMF. So 6 over 8. I2. We can calculate I2 by subtracting or by applying the Ohm's law. 6 over 4. Of course, these are very simple examples, but tomorrow we're going to do more complicated examples. The strategy, the way of thinking doesn't depend on how many elements are in a circuit. All right. The energy. Now, don't answer this question. We have 5, that's enough. Just tell me what you think. You are at home, you have many different devices. For example, here I have 2 very simple devices. I have to plug it into power outlet. Okay, it's on. I have to plug this one. People get Oscars for something like that, if you know what I mean. So, that one is plugged in here, this one is plugged in there. What kind of a wiring? What kind of a connection? What do you think? What do you think? What do you think? Parallel. They all outlets, they all go to the same power line eventually. They're all connected in parallel to each other. And in parallel. And this is how you pay your electric bill. Each device consumes some power. And if you use it for an hour or 10 hours, you just calculate total amount of work that device does. For the first device, power times, you used it over a month. Second, you calculate the total energy spent, and you multiply by how much you pay for. And this is what people get confused about. This is a practical unit, not physical. Kilowatt hour. That's how it's measured. We pay for a kilowatt hour. But kilo means 1,000, watt means watt, hour means 3,600 seconds. So this is just amount of joules. For this amount of joules, we pay, well, it depends on your provider, 4 cents, 6 cents. And that's how they calculate your bill. This is how they all connected eventually to the same line. And again, this is not a question. You just saw 2 bulbs. One was bright, second was dim. Of course, the brighter consumes more power, the dimmer consumes less power, and actually it emits more power or less power. So the dim one was 40-watt bulb, the bright one was 100-watt bulb. But only because they connected in parallel. And my last, again, that's not the question, last thing I want to show you is this. 40, 100. So I'm going to switch to a camera soon. This is very important to understand that changing the type of wiring changes things. Right now, here, these two bulbs connected in parallel to each other. Of course, I need a wire to connect them to a power supply. Plug it in and turn the switch on. Well, you can see this is brighter, this is dimmer. 140. Now, I want to rewire the circuit. I want to connect the same bulbs in series. What do you think should happen? In series means like this. And I need to connect my leads like this now. Plug it in. Completely opposite. The 100-watt bulb is practically doesn't do anything, but the 41 bulb now is brighter. What is the explanation? The explanation is in calculating the power. If we calculate the power, more power means brighter, less power means dimmer. And all we have to do is, it's alive. All we have to do is just calculate power twice. First time, when we have R1, R2 bulbs connected in parallel, second times the same bulbs, R1, R2 connected in series. Power 1 will be equal to delta V squared over R1. Power 2 will be equal to delta V squared over R2. Here, power 1 will be equal to current times R1. And power 2 equals current times R2. But the thing is, the current here and the current there are not the same. Not the same. So parallel, series, and that's it, what I'm going to say about it today. So I'm going to pick up from this tomorrow. That's my alarm. Again, from the point of view of theory, you know everything. And we are not going to learn anything new tomorrow, just more examples, more examples, more examples. Good morning.